Okay, so I'm Pelayo Peñarroya, and I will be presenting my trailer to the PhD defense, hopefully to be defended in a couple of months. The title is Intelligent Navigation and Control System for Minor Celestial Body Descent and Ascent, and my supervisor is Manuel Sanjurjo, although I haven't put him here in the title, but he still is. Very quickly, and very similar to the previous presenter, I'm trying to put together here a presentation to talk about the narrative of the research and not so much on the technical details, because this has been presented in previous years, and of course you can always contact me for these details. But my main point today is to talk to you about the state of the art, how the gaps and objectives were chosen and selected, and how the different publications in the case, because I'm also doing a thesis by papers, fulfill these gaps and objectives, and what contributions they represent, right? And I will have some conclusions on the technical side, but this is not the main point of the presentation today. So some state of the art, I want to divide it in three sections. First one being the world context, as I call it, then space missions, and then available technology. So for the world context, I think like this talks about whenever we do some research, we need to ask ourselves, what is it for, right? So in my opinion, the world is changing right now. We are going through a time of profound transformation, and this is mainly led by the rise of autonomy. This has been happening for the last decades, but I feel like nowadays we experience it much more in a tangible way. With, for example, autonomous cars, the usage of LLM, so large language models, and so on, they tend to group together tasks that are, or used to be programmatic, and now they are less and less programmatic, but they can still be performed autonomously. And they take off this burden from us so we can focus on further details. So by following this, I feel like this is the way I wanted to put my research so towards autonomy, right? Then I also feel like there's this sort of tension between preservation and expansion, because with more autonomy, we are able to go farther in all of our research lines. But also there's this mindset, I believe, right now of resource usage, also in terms of sustainability, earth, environment. But in general, I feel like we're trying to use technology in lower devices, for example. Lower devices, when I mean lower, is like more simple devices, and bring this technology to platforms such as, for example, CubeSats, right? So this is a bit of the starting point I was at when I started this research. Of course, I try to learn as much as possible from previous missions. Here we see missions like the Near Shoemaker, Hayabusa ones. This got a laser, right? Yeah, the Rosetta mission, OSIRIS-REx here, and also the DART era kind of compound mission. All of these missions tackle the problem of collecting samples, for example, from minor celestial bodies, both asteroids and comets. And even the DART mission is also even creating a crater on a body and then studying it. So really a lot of interaction with these bodies. So from these main missions, there was a lot of technology that was developed for that. And this is something that I also wanted and needed to understand. So which are the main cornerstones of the technology developments that I can start from? With that, I try to summarize it here with these three blocks. First one being hazard detection. If you plan to have something autonomous, you need to somewhat understand what you're looking at. So this has to do with hazard detection. Most of the techniques that we see nowadays, and the ones that have been used, rely on LiDAR, so light radar, so to say. And also infusing data with optical sensors input via standard gamma filters, typically. So this is a complex task that also requires a complex instrument. Then, of course, the usage of neural networks. This has been something that Alfredo, for example, has been introducing before. They are light and fast. They require some training, but they can learn very complex tasks and then execute them in a lightweight environment, such as onboard processors. And then integrated systems. Of course, you are as fast as your slowest component. So if you need to be autonomous, you cannot have like a navigation system that's super autonomous and fast, but then your guidance subsystem is not capable of keeping up with this pace, no? So it has to be like a fully connected GNC system. So with that, we found what I call here the work to do, right? So these are sort of the gaps that are present still in this field. First one being the absence of an integrated GNC, what I just mentioned. we still have a lot of Earth-based facilities for decision-making and control. There's also a big LiDAR dependency when it comes to surface terrain understanding and recognition. LiDARs are big instruments that limit even mission design in terms of platform, in terms of power consumption, so they are really constrained for a mission. Then, of course, the computational demand is always something that you need to have when you are doing some autonomy or autonomous activities, because there's a frequency loop that you need to run as fast as possible to be able to feed from the environment as frequently as possible. And then inadequate passive systems. Most of them rely on pre-mapped terrain data, which might not be available if we are talking about exploration. And then sometimes they are also not accurate for small celestial bodies. So with that, what we did is we defined this sort of network of gaps and objectives. For now, I want you to look only to the first two rows, so gaps and objectives. And we defined gaps from 1 to 5 and objectives also from 1 to 5. Gaps being complexity in asteroid, hazard detection and avoidance, and multidisciplinary integration, trying to bridge the gap between complexibility and accessibility, linked to these previous points I mentioned. And then the three other goals are more related to specific publications that I'm going to be showing in the following slides. So passive hazard detection and avoidance systems, onboard gravity modeling, and the absence of a fully autonomous system. Consequently, the objectives follow these goals, and they are not univocally connected, but some of them, as you see here in the diagram, are affect to some objectives, more than one, let's say. Oops, sorry. So okay, now I'm going to go through the papers, 3 papers I've got. First one talking about landing simulations, second one about hazard detection and avoidance, third one talking about a fully autonomous GNC system methodology. Paper 1. This was performed during a secondment at Politecnico de Milano. This is maybe the one that's less connected to the other two, but led to the second one. So I still think that is pretty much connected to it. In here, what we do was using accessible technologies and tools, such as, for example, Blender in this case, to perform landing simulations with contact dynamics. So we were dropping a CubeSat, as for example, the Milani CubeSat was dropped by the DART mission in a crater, which we didn't know which shape, which morphology it was going to have. So we tried different morphologies for the crater, as you see here in this upper left plot. And then we're creating via simulations in Blender that were validated in the proper environment, these landing maps, where we would do like Monte Carlo simulations with lots of drops and trying different attitudes and defining different areas of success, which are defined by scientific objectives or whatever other objective you've got. You define which points can I touch down with which attitude, so that once I rebound, and I roll and settle down in the area that I want to settle down, because then maybe the CubeSat collects a sample or does something like that. So with that, the idea was to create lookup tables that can be implemented on board and can be used autonomously to understand where to point my CubeSat and where to throw it, let's say, right? What do we contribute to with this paper? So contributions 1 and 2. So a comprehensive simulation framework that, as you see, affects all of the publications, because all of these simulations are mostly linked together. So the simulation framework comes with it. And then in-depth landing simulation insights. So this gave us a lot of understanding of how landing simulation works, the intricacies of it, and where do we want it to go next. Connected to that, paper 2. This is a LiDAR-less approach to hazard detection and avoidance systems. What do we do here? So using convolutional neural networks, similar to what Alfredo presented. Thank you, because you explained a lot of the technical details, as always. It's a pleasure to have you before me. Here we train some networks to generate what we call safety maps. Okay, we divided this, or we stratified this in 3 layers: one for feature detection, shadow detection, and slope estimation. Slope estimation is where the actual research gap is, because we are not dependent on LiDARs anymore, because we don't depend on 3D models or 3D point clouds, but rather on images, 2D images. So we infer information about volumetry, if that's a word, from 2D images. So with that, from the left-hand side, we take an image, which in this case is a synthetic image, we generate it with a pipeline we developed. And we have in rows feature detection, shadow detection, and slope estimation. And in columns, we've got the target, let's say, the prediction, and the probability mask. So combining them together with some thresholding, we managed to obtain what's called a safety map. Of course, this safety map is very much unlinked to where we are. So how do I know then how to get here if I don't know where I am, right? Again, this paper contributes to well, contributions one, still simulation framework, but now also to the passive hash detection avoidance system and picking up information and filling gaps from gaps 1, 2, and 3. So taking back the question I posed before, how do we connect this to landing? Yeah, I'm closing up. Paper 3 comes in, right? And here collaborating together with Alfredo and with Thomas, who graduated, I don't know, like defended his thesis some months ago already. So congrats, Thomas. We developed a fully connected GNC methodology where we take these safety maps and using the navigation information from Alfredo's network, we perform, using ray tracing techniques, a projection of this safety map onto a longitude-latitude map that as we explore the orbit with these reconnaissance orbits, fill up what we call the global safety map. Once you have orbited your body for a time, a particular time, the arbitrary time that you need to explore this body, you have a full map which you can use to create a safety mask. In this case, for example, was only, so what you see in yellow is pixels or longitude latitude coordinates that are farthest away from hazard areas, which are represented in red here. So with this map, basically the spacecraft is autonomously taking image, autonomously knowing its position, autonomously generating the safety map, and autonomously making the decision or taking decisions to understand where to land. Yeah, this contributed to also, well, contributions 1 and also 4 in this case that collected information from the essence of a fully autonomous GNC system. Collective conclusions for the 3 papers. We managed to show how usage of more accessible tools is something that can be done for more complex simulations, generating landing map predictions. Also, we developed a technique that relies on passive sensors, which is a huge improvement because this opens the world for resource-constrained platforms, such as CubeSats, for example, making it much cheaper and accessible for different platforms to use. And then we showed how this methodology works in a fully connected autonomous GNC system, together with Alfredo's navigation system and Thomas' guidance and control, model predictive control system, let's say. Still some things to improve. There's always room for improvement. So for example, we could integrate navigation in the landing simulations. We would also like to go for a full hardware validation, even though we tried these models already in a Raspberry Pi and taking images with a Raspberry Pi module at another secondment at DFK Bremen. And then, yeah, for the fully autonomous system, we need to put it in a more real scenario where we also have uncertainty and contingency analysis, typical TRL racing processes, right? But this doesn't really belong to research anymore. And that's it, pretty much.